Okay. Hi, everyone. Thanks for attending my talk. My name is Martin Robinson. I'm the head of the Research Software Engineering Group at the University of Oxford. So today I'll be talking about a Rust crate I've been writing over the last couple of years called Diffsol, which is a crate for solving differential equations. So let me just go to the slide. So what is Diffsol? Diffsol solves equations in the following form. So we've got a rate equation here, dy dt equals some function of time, t, a state vector, y, and a vector of parameters, p. You've also got a mass matrix there. Non-singular mass matrices are useful for some PD discretizations. And if you allow for a singular mass matrix, then you can also incorporate algebraic equations for things like constraints. So to solve these types of equations, Diffsol has three different solvers implemented. One is a BDF solver, which is useful for stiff equations. There's an SDIRC or ESDIRC solver, which is useful for moderately stiff equations. And then there's an explicit Runge-Kutta solver for non-stiff equations. So with the Runge-Kutta solvers, there's a few tableaus included that you can use, or you can just bring your own tableau to use with the library. So each solver allows you to use matrices, vectors, and linear solvers from either the AnAlgebra or FAIR crates. They all have adaptive set size error control with user-defined tolerances and can interpolate solutions to any time point. There's a high-level solve API, which is fairly familiar if you're coming from things like SciPy or MATLAB. But you can also manually step the time and deal with things like events by mutating the state and stop at particular times and things like that. So you can supply an optional output function, G, which you can integrate over time as well as the ODE equations. And you can also perform forwards and adjoint sensitivity analysis as well. So the most important thing about an ODE library is how do you supply your actual equations that you want to solve. So there's three different ways of doing this with Diffsol. So first, you can use a simple string to represent your equations using a domain-specific language, which I've called Diffsol. So this is quite useful for using Diffsol from a higher level language like Python, for example. If you want to stick with Rust, you can use Rust closures to represent your equations. And for maximum flexibility, you can also just use your own structs by implementing the ODE equations trait, which I'll talk about a bit more in a couple of slides. So as an example, this is the logistic growth model up the top here. So it's just a one-line ODE. Has a couple of parameters, R and K. And so we've got some code here to solve it using Diffsol. So we can specify a matrix type that we want to use, a linear solver type, and to compile the Diffsol equations, we're going to use LLVM here. And so we use this ODE builder to both set the parameters that we want to solve for, but also supply the equations as well. And so this goes away and gets compiled, JIT compiled by LLVM. And so once we've got our equations, we can create a solver. Here we're going to use the BDF solver and give it a linear solver as well. And then solve our equations up till t equals 40. So if we want to do the same thing, but using Rust closures, we'd do something like this. So the main difference here, besides the fact that we're using Rust closures, is that we're also supplying an additional equation, which is the Jacobian vector product of the right-hand side of your equations. So you need to add this because you're using an implicit solver, the BDF, which requires this Jacobian information. Okay, so I wanted to talk a bit about the architecture of Diffsol. So it's made up of a collection of traits, and this allows you to swap in and out different vector or matrix types or linear solvers or ODE solvers, for example. So you can sort of organize them into three layers, I guess. So first layer, you've got a collection of linear algebra traits, so representing things like scalars, vectors, sparse matrices, and their operations between them. Second layer is, I'll call it this operator layer. And this represents just arbitrary mathematical functions, so f of x, and associated linear solvers and nonlinear solvers. And then finally, you've got the ODE equations trait, representing things like dy dt equals f of x, and associated solver trait for these types of equations. So for the operators, so Diffsol uses the concept of an operation or a mathematical function f of x in a few different places. So both for representing the ODE equations themselves. So for example, the right-hand side is a nonlinear function. And also for the implicit solvers, for example, you could think of them as a series of nonlinear solves of a particular function, which is a discretization of your original ODE equations. So so at every time step, the Diffsol needs to solve a nonlinear equation, and it does this using a Newton iteration method most of the time. And that nonlinear solver also requires a linear solver. So there's traits for linear solvers as well. So as well as traits for things like nonlinear operations, there's also subtraits which include things like the Jacobian vector product for that function, or the sensitivity vector product as well. So then the layer above that is you get the ODE equations trait. So this reuses all of those operator traits to represent your set of equations. So I've reproduced this trait here, and you can see there's a collection of associated types here for the right-hand side equations, the initial conditions, the mass matrix, which is a linear operator. And so you can see this sort of builds up your set of ODE equations. So these are the traits that you need to implement if you wanted to use your own structs to supply your ODE equations. Obviously, like Diffsol tries to hide this away as much as possible and allow you to use things like the Diffsol, domain-specific language, or Rust closures. But it allows you to implement these traits for sort of maximum flexibility. So once you've set up a trait like this, it allows you to do a few interesting things. So for example, you can create different types of equations that different solvers require. So for example, implicit solvers, you need the additional Jacobian information for your right-hand side. So here we can create a subtrait, ODE equations implicit, and bound the right-hand side associated type such that the Jacobian information must be implemented as well. So this is quite nice because it allows you to, so if the user doesn't supply the Jacobian information, then if you try to use an implicit solver, then it'll give you a compile time error rather than a runtime error. And you can do the same things with different types of equations, such as the equations you need for things like forward sensitivity analysis and also adjoint sensitivity. So then you've got the ODE solver method traits. So all the ODE solver methods in Diffsol implement this trait, and it basically forms the public API of the library. So with all the solvers, you can sort of interrogate the state, you can mutate the state, you can step the solver forward in time, you can interpolate backwards in time, as well as a few other things. And there's some higher level provided methods here as well. So, for example, solve, which solves your equations over a period of time and returns you the entire solution. Okay, so the so the the architecture of Diffsol gives you a lot of flexibility, and as it says, it allows you to swap in and out different things like linear solvers and equations and things like that. It makes it all quite modular. Um, Diffsol makes heavy use of generic types to keep the performance while still maintaining this sort of flexibility. Of course, this sort of comes with a few downsides as well. So a lot of the type information is quite complex, and satisfying the trait bounds can be quite difficult at times and give you some quite complicated compiler errors. It's nowhere near as bad as C++ templates, for example, but still not great. Ironically, given like the whole point is to make it modular and don't repeat your code, but there's a lot of repetition in things like trait bounds across multiple implementations, and the lack of default associated types in Rust is also gives a lot of repetition as well. Although this should be fixed fairly soon. And also linting. So Rust Analyzer is struggles a lot to parse all the types and the trait bounds, and it usually takes quite a bit of memory, and I have to constantly restart it. So that's something I struggle with a bit as well. But overall, really happy with the architecture of Diffsol. So really happy to sort of talk about it with anyone who's interested. So just hit me up in the discussions section. I'm more than happy to keep talking about it in more depth. Cool. So I'll stop there and yeah, open it up for questions.
Thank you very much, Martin. Well, we have time for, I think, one question. And there's another question in the Q&A that maybe you can answer there. The question says, have you benchmarked this against other popular libraries such as Sundials?
Yes. So if you go to the Diffsol book, so if you go to the repository, there's a link to an MD book I put together for Diffsol, and down the bottom of there, there's some benchmarks against sundials. So I was mainly interested in benchmarking against sundials since that's what I've sort of used in the past, and it's fairly comparable. Some equations sundials does better, some equations Diffsol does better. So it does depend on the particular set of equations that you're solving. Another thing I guess to say is that so if you use the Diffsol domain specific language, it adds a little bit of overhead, but it's not a huge amount. Like compared to using Rust closures, it's fairly similar. Like you may get a few percent decrease in performance, but it's still pretty good. Yeah, so other benchmarks that are in the Diffsol book are against a JAX solver library, Diffrax, I think it's called, and also another Python library, or it's Python C++ library called Casadi. So yeah, there's a few benchmarks on the website.